Hi, welcome once again to Math as a Second Language. Last time we essentially completed our treatment of the arithmetic of whole numbers. My next two lessons presentations will be, I guess we could call them enrichment. It's going to be on different number bases, and there are going to be two of them. The first one mirrors my theory that students would do better with understanding place value if the trade-in value had been less than 10. In other words, I think that one of the reasons that students have trouble learning the tables and everything is that there's too many digits to remember. So I want to see what would happen if we taught place value by introducing it in a way where you didn't have to wait to get up to 10 before you traded in. The second one is sort of a cathartic one, where for you as teachers to get a better sense of what young students are going through when they're learning the tables. A lot of times we say, what's so hard about learning the tables? So what I want to do is to present a different number base for you to think in, and to hopefully by doing that, get a feeling as to what kind of problems a youngster may be experiencing as they try to learn the tables, okay? Let me introduce this in a rather strange way. You almost have to see it. Well, it'll sound even stranger if I say it. And this place value depends on the fact that we have 10 fingers, but it has nothing to do with the fact that we have 10 fingers. I hope that sounds like enough of a contradiction. Let's see what it looks like in writing. Place value depends on the fact that we have 10 fingers, but not on the fact that we have 10 fingers. Notice the subtle difference. The first time I refer to 10, it's as a numeral 10. The second time, it's the word 10, T-E-N. And the word 10 stands for this many, okay? The symbol 10 depends on what the trade-in value is. For example, it was very natural that the Romans picked 10 for a trade-in value because they had 10 fingers. What if they had decided that, hey, it's enough to keep track of the fingers on one hand? Suppose they had decided that instead of trading in by 10s, they were going to trade in by 5s. So in other words, the I would still represent 1, but now the X would represent 5 I's, 1, 2, 3, 4, 5. So now when they wrote XXXI, it's still 3 X's and an I, but based on how we would write it, it stands for what now? 3 5s and a 1. That would be the number 6 that we call 16. The arithmetic will be the same, the numerals would be different. Well, with that in mind, let's see why students may have trouble learning the tables. I like to think in terms of an automobile odometer. It's where it really shows strikingly how you only need the digits 0 through 9 to express any whole number. See, how does an odometer work? It's a cog, a gear, with 10 faces on it, 0 through 9. And as you go through each mile, this moves up by 1. And when it comes back to the 0, it clicks the cog next to it by 1. In other words, every time the 0 comes up, this clicks by 1 more, and this gives you a visual way of seeing how the numbers are generated. At any rate, using these 10 digits, actually the 0 is kind of easy to work with, but still, this is the table that the average youngster is supposed to learn, and it looks pretty easy to us because we've used it for so long that it seems quite natural. Okay? What I would like to do instead now is, let's suppose we had an odometer that had only 2 faces on it, a 0 and a 1. Look, to do mileage, you have to have at least 2 symbols. You need a 0 as a placeholder, and you also need a 1 to generate each mile as you travel. The only difference is going to be that with a base 2 odometer, the only digits you see are a 0 and a 1. Every time the 0 comes up, it clicks the next gear by 1. So let's take a look and see what would happen. Let's suppose in an automobile, there's side by side a base 2 odometer and a base 10 odometer. The base 10 odometer we're pretty much used to. You drive 9 miles, it goes 1, 2, 3, 4, 5, 6, 7, 8, 9. What happens with the base 2 odometer? After 1 mile, you see 0, 0, 0, 1. What happens with the next mile? The 0 comes back up again, clicks this guy by 1, and so what you would see is 0, 0, 1, 0. What happens with the next number? See, focus on these individually. After the 0 comes up a 1, so everything else stays the same. See? What happens with the next smile? Well, the 0 comes up, that clicks this guy by 1, that brings him back to 0, and it clicks the next one by 1. So do you see the counting here? In other words, this may look kind of strange. You may want to look at this and say, how can 101 be the same as 5? The difference is this is 5, this is not 101. It's 101. And in terms of our own language, it's a 1, no 2s, and a 4. That's just, okay? In other words, the numerals are different. But do you really drive a different number? Does it make any sense at all to say, wow, look at, if I went base 2, I drove 101 miles, but base 5, I only drove 5 miles. The mileage is the same. So what would happen in a situation like that is, look at how these numbers are, and now we'll arrange them in a number line. This is the number line. See what happens? After 1, you add on 1, that becomes a 0 and a 1. Now you add on another 1, etc., etc. And we're going to look at this in a different way in a few minutes. Look how simple the arithmetic tables become. All you have to do now is learn the tables for 0 and 1. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is still 1. 1 plus 1 is 1. I'm not going to say 10 here. 1 plus 1 is 1, 0. See what this is? This is not 10. It's 1, 0. In other words, the trade-in value in place value will always look like 1, 0. What's the multiplication table? 0 times 0 is 0. 0 times 1 is 0. 1 times 0 is 0. 1 times 1 is 1. That's the end of it. And if we were going into this in more detail, I would do some arithmetic in base 2. But I'm just trying to put across the point now how much simpler it might be for kids to get used to trading in the same amount of each denomination for one of the next higher denomination. So for example, I would like to see what happens if you were to introduce a game called playing shopkeeper. See, what I'm afraid of is students at a very young age are going to be confused between the numeral 10 and the word 10. Somehow they're not going to look at 10 and say, oh, it stands for 2. So I just want to sort of do this a different way. Let's suppose that we were in a country where we still had place value, but for whatever the reason was, we didn't want our monetary system to be the same as place value with base 10. What we decided to do was to do everything in terms of trading in by 2s. In other words, you could have a $1 bill. As soon as you want to get to $2, you'd have a $2 bill. In other words, instead of having a $1 bill, a $10 bill, $100 bill, $1,000 bill, we would go up by 2s instead. And notice that I can write 2, 4, 8 in this system because I'm still dealing in base 10 as far as our number system is concerned, but the students are now thinking of the monetary system in terms of our regular base 10 system. So in other words, if you have a $2 bill, 2 2s would be a 4, 2 4s would be an 8. So what would happen is, as soon as you wanted to pay $2, you could trade in the 2 $1 bills for 1 $2 bill. How would you pay $3? It would be the 2 and a 1. How would you pay for $4? Well, the 2 1s would convert into 1 more 10, 1 more 2. Having 2 2s would convert into a 4. And so you would pay for a $4 purchase by 1 $4 bill. How would you pay for a $5 purchase? You say, well, I can take out a 4. That would leave me with 1. So I can now pay with a 4 and a 1. How would I pay 6? 4 and 2. How would I pay for a 7? 4, 2, and 1. How would I pay for an $8 purchase? I'd give them an $8 bill. How would I pay for a $9 purchase? I could take out an 8, and 1 more would give me the 9. And what I thought might be interesting is, I don't need the zeros in here because the denominations are still visible. But suppose I put them in. And you see what's happened here? I've built the base 2 odometer all over again. See, you don't read this as 100. You now say, I don't have any 1s, I don't have any 2s, but I have a 4. I have a 1, no 2s, and a 4, etc. And so you get used to the idea that you're trading in by twos. I think this is much easier for a youngster to see than having to get all the way up to 10. Of course, at the preschool level, the kids might not even know their numerals as such. So I thought you could play a different game. You could represent, say, the $1 bill, maybe teach the kids the colors of the rainbow: red, yellow, orange, green, blue, purple. What you do is the red would be the $1 bill. Every time you had two reds, you could trade them in for a $2 bill, which would be represented by an orange tile. Every time you had two orange tiles, you could trade it in for a yellow tile, which would represent the $4 bill. The $8 bill might be done in green, see, red, orange, yellow, green, and it would be what? Two $4 bills, okay? So you don't even have to mention money. You say every time you have two of these, you trade them in for one of these. Every time you have two of these, you can trade them in for one of these. Every time you have two of these, you can trade them in for one of these. So you can either say, I have this many dollars, which we would count as what? 1, 2, 3, 4, 5, 6, 7, 8. And we say, let's trade in. Well, every time you have two reds, what can you do? You trade them in for an orange. I think kids can keep track of this. What happens with the orange? Every time you have two orange, you can trade them in for a yellow. Okay? So now what's happened? All of these reds have been replaced by two yellows. And what can we do with the two yellows? Replace it by a green. And what happens? 8 ones turns out to be 1 8. But my feeling is that the youngsters can count by twos much easier than by tens. And they're still getting the feeling of what? I'm trading in the same number of each denomination to get to the denomination that's one greater. And if that becomes too simple, or you're dealing with an old age, nothing says you have to trade in by twos. You could trade in by threes. How would you do that in terms of a monetary system? Well, you have the trade-in value being 3. You have a $1 bill, a $3 bill, a $9 bill, and a $27 bill. The next one would be what? 27 times 3, or 81. Now what would happen in terms of the colors? 3 reds would be an orange, 3 orange would be a yellow, 3 yellows would be a green. So what happens over here? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is that right? 2, 4, 6. So we have 10. And now what's going to happen? Every time we have 3 of a denomination, we can trade it in for one of the next one. So for 3 reds, I can get an orange. 3 more reds, I get another orange. 3 more reds, I get another orange. And I still have a red left. Now what can I do? Every time I have 3 orange ones, I can trade them in for a yellow. Okay? So what does the yellow one stand for? The yellow one is 9. See, these are 1, 2, 3. So you have 3, 6, 9. See, the yellow one is 9, the red one is 1, and you still have 9 plus 1 is 10. What I want the youngster to get the idea of is you can trade in by 2s, by 3s, by 4s, by 5, whatever. To see that the miracle of place value has nothing to do with the fact that we had 10 fingers, but rather that we always trade in the same amount of one denomination for the value of the next higher denomination. Now, what happens a lot of times when I do this in workshops, teachers will say things to me like, this is a wonderful way to do it, but the curriculum is so crowded, we don't have time to do that. We have to do it the way it's prescribed. Now, I'm not going to argue too much about that. What I am going to say is something kind of interesting in my own mind. When you learn by rote, I'll make a little graph here. And I highlight this by saying it's a highly subjective opinion. This is just my opinion, and I just happen to come up with this opinion based on 50 years of classroom experience. When you teach things by rote, at the beginning, things are pretty easy. You learn pretty fast. But what happens is, as your mind becomes cluttered, things become more and more confusing, and the learning curve levels off. I think In mathematical terms, we would say that this graph is logarithmic, which would scare enough people. For layman's terms, think of this as a roof. And this would be a roof that sheds water. In other words, the rain hits the roof and it rolls off. Okay? It starts steep and levels off. Now, what happens when you learn logically? It's very difficult. You're getting the fundamentals. You start off very, very slowly, but as you build up the logical connection, as you start to understand the why versus the how, the learning curve becomes faster and faster. And what happens is eventually the logical way of learning by understanding, overtakes learning by rote. What happens is the curriculum is so crowded that we become impatient. And what do? We chop off the experiment someplace before the two curves crisscross. What I'm trying to point out is if we take the time to develop this stuff logically, you'll be amazed by how fast the rest of the curriculum goes. When we finish the next enrichment lecture, I'm going to start fractions, and you're going to see how much of fractions has already been done by our whole number arithmetic. I think that's going to be a very, very surprising thing, that once you know whole number arithmetic, every problem that involves fractions can be replaced by an equivalent whole number problem just by using the adjective noun theme. But I think that's taken us far enough for today. So I thought I would come to our usual practice problem, where I'm going to ask you to pause the video, look at the problem, and then after you've worked on it, whether you've got an answer or you give up and want to know what is the answer, come back and watch the rest of the video. But here's the practice problem. Use base 2 to verify the following assertion. If you start with 1 and add consecutive powers of 2, starting with 2, the sum will always be 1 less than the next power of 2. Look, let's suppose we add up all the powers of 2, starting with 1 up to 8. 1 plus 2 is 3, plus 4 is 7, plus 8 is 15. See, 1 plus 2 to the first power, plus 2 to the second power, plus 2 to the third power. That's 15. 15 is 1 less than 16, and 16 is 2 to the fourth power. Okay? What happens if we add 15 and 16? We get 31. And 31 is what? 1 less than 32, which is the next power of 2. And the question is, why does this happen in terms of base 2 arithmetic? And turn on the video when you're ready to see the exciting conclusion of today's lesson. Let's look at base 2 arithmetic. Okay, think of the odometer again, where you are thinking in terms of buying stuff with money. Either way, how would you represent 1 plus 2 plus 4 plus 8 in the system? You have a 1, a 2, a 4, and an 8. What happens with the next one that you add on? The 1 plus 1 becomes 2, which gives you 1 more 2. The 2 2's give you a 4. Okay? The next one gives you this, and that adds up to the next one over here. It's the same thing as a little kid. I used to love to watch the odometer on the car when everything came up 9s. Because once all the 9s came up, what happened? The next mile, the first 9 would turn to a 0. That would click the next one. That 9 would turn to a 0. I'd click the next one. That 9 would turn to a 0, etc., etc., etc. Well, the same thing is happening here with base 2. Every time you see all 1s, what's going to happen with the next mile? All the 1s will be replaced by 0s, and there'll be a 1 in the column that comes next. Again, interesting things, I think, to internalize, to begin to realize how much of place value depends on the trading in concept, but not on the amount that we're trading in by. And again, that brings us to the conclusion of today's lesson. And next time we'll continue with a slightly bigger base. We're going to deal with the one we started with at the beginning of this lecture. We're going to reinvent history the history of place value based on what would have happened if the Romans had traded in by 5 rather than by 10. This is going to become the trade-in value for our next lecture. But until then, have a great time, work hard, smile a lot, and I'll see you next time.